In this video, I want to talk about the Gram-Schmidt process in general for arbitrary inner product spaces, and we can word this as a theorem. So the Gram-Schmidt theorem or the Gram-Schmidt process says that every finite dimensional non-zero inner product space has an orthonormal basis. We need finite dimensional, and then the non-zero is there because if you have the zero subspace, the basis is just the zero vector. There's no way to normalize that vector and make it length 1. Okay, so that's really the only outlier here. So any other finite dimensional non-zero inner product space has an orthonormal basis. The proof that they give for this fact is constructive. It's actually how we basically we took the Gram-Schmidt process that I'm going to present to you here. We applied it to the special case of dot products, and that's what we did in previous videos. Here I'm going to show you how this works in general. It's going to be very similar. So not too much is going to be new here. There is a little bit of new notation that I want to talk about. So we're used to the idea of talking about projections of a vector onto another vector. So for example, if we have two vectors here and we have u and v are in some inner product space, then the projection of v on u is defined as the inner product of u and v divided by the length of u squared, or the inner product of u with itself, times the vector u. Okay, so this is some scalar times u. So that's the projection of v onto u. And that's an old idea. I mean, we talked about this in the special case when the inner product is the dot product, right? So we work this out in general. But this is the projection, how this works for arbitrary inner product spaces. And more than that, what I want to do is tell you if you have a subspace W of your inner product space V. So V is going to be our inner product space, W is some subspace. And if I take some vector V, okay, so if little v is a vector in big V, then we can also project V onto the subspace W in the following way. If W has a basis, let's write it like this. Let's say that the basis for W is, say, W1 up to Wn, say it's an n-dimensional subspace. Then what you can do is you can define the projection of V onto the subspace W in the following way. So what you're going to do is you're going to add up the projection of V onto each of the basis vectors. So what that means is you're going to take, let me write it out in two different ways here, but you're going to take V and project it onto W1. So you get the inner product of V and W1 divided by the length of W1 squared times W1, plus the same where you replace W1 with W2, all the way up to V times Wn divided by the length of Wn squared times W1. Okay, or if you want to write it more succinctly, and this is how I'll think about it in the future, but this is just the sum from I equals 1 to n. This is just a notation thing. The inner product of V with Wi divided by the length of Wi squared times the vector Wi. So this is the projection of V onto the space W. And it turns out that the projection of V onto a vector is the same as the projection of V onto the space W, where W is just the span of that single vector. So this is the span of the vector U. These are all capital W's. Okay, and so you can think of the projection of a vector onto another vector as the projection of that vector V onto the subspace spanned by that vector U. That's another way to think about the projection. Okay, and this is how we generalize to the projection of a vector onto a subspace. If it turns out, and you can kind of think about this, if the vector V that you're starting with is in W to begin with, then the projection of V onto W is just V. Okay, so if you kind of think about, you have a subspace here. So here you have a subspace, which I'm drawing as a plane. If you were to take a vector in that plane, so imagine it's actually on that plane, the projection is just going to be itself. And in general, if you take a vector that's not on that plane, let's make it pink, it's going to be some vector like this. And the idea is that when you project down to the plane, you get that red projection vector. But if it's on the plane to begin with, the projection is just itself. Okay, that seems reasonable when we think of this as kind of, standing with a flashlight and seeing the shadow that the vector makes on the subspace. That's basically what we're doing here. Okay, and so that's the idea. So this is the vector v, and then the red vector is that projection vector that we were talking about. So this is the projection of v on w, where w is this planar subspace. I drew it as a plane because that's all I can draw, right? So that's the idea. That's a projection of a vector. That's the projection of a vector on a subspace w. All right, with that under our belt, what we can do is we can describe the Gram-Schmidt process in general. So the way that Gram-Schmidt works, the way that we kind of construct this orthonormal basis is we can actually, physically construct it. So this is a really nice proof. A lot of times in math, you can just say that there must be some orthonormal basis, but it doesn't necessarily help you find it. In this case, the Gram-Schmidt proof is a constructive proof. It actually helps you construct that orthonormal basis. And so anyways, this is what's called a constructive proof. So let's say that the inner product space that we're working with, V, has a basis, say V1 to Vn. Okay, so that's our basis. I'm going to call that B. So that's our basis for V. What we're going to do is we're going to construct the orthonormal basis from that. The hard part being constructing the orthogonal basis. And then once you have orthogonality, you can just normalize each of the vectors, and then you get orthonormal basis for just one small extra step. So the idea is, if I take V1, that's just going to be what our U1 is. So U1 is just V1. And U2 is going to be the projection of, so it's going to be V2 minus the projection of V2 onto W1, where W1 is the span of U1. U3 is going to be V3 minus the projection of V3 onto W2, where W2 is the span of U1 and U2. And then you keep repeating this process. U4 is V4 minus the projection of V4 onto W3, where W3 is the span of U1, U2, and U3, and so on. Okay, eventually you get to UN, which would be Vn minus the projection of Vn on that corresponding subspace from one step up. So here Wn minus 1 is the span of the vectors U1, U2, U3, all the way up to UN minus 1. Okay, so that's Wn minus 1. So this is the Gram-Schmidt process. What I want to do is let's actually see this in motion. We've basically, oh, I'm sorry, that's like 95% of Gram-Schmidt. That's the orthogonal basis. So U1 to UN is the orthogonal basis. And then you can let E sub I be U sub I over the length of U sub I. And then the orthonormal basis is those vectors E1 to En. Okay, that's the idea. So let's see this in action. So what I want to do is I want to take let's take V to be the vector space of the polynomials with real coefficients of degree 2 or less. And our inner product here is going to be the integral from 0 to 1. Okay, so the integral of f times g from 0 to 1. And what I want to do is I want to start with a standard basis. So let's start with the basis 1x squared. Okay, so that's our standard basis. But it turns out that that's not an orthonormal basis. They're not orthogonal. Okay, so if you take, for example, the inner product of 1 with x, you get 1/2. You get the integral of x from 0 to 1, you get 1/2. And so those are not orthogonal vectors, and therefore you can't get an orthonormal basis just by dividing the lengths. You have to construct that what word am I thinking of? You have to construct the orthogonal basis. Sorry. So let's do that. So U1 is just going to be V1. So no questions there. That is already unit length because we're integrating the constant 1 over an interval of length 1, and therefore we'll have area 1. So that is luckily already unit length. U2 is going to be V2 minus the projection of V2 on W1, which is the projection onto just U1. We can think of it that way. And if we compute what this is, remember that the projection of X on U is going to be the inner product of X with U1 divided by the length of U1 squared times U1. And U1 here is 1. So this is going to be X minus the inner product of X with 1 divided by the length of 1 squared times 1. And so this is going to be X minus, let's see, the inner product of 1 and X is the integral of X from 0 to 1. So that's 1/2. The inner product of 1 with itself is going to be 1. So squared is still 1 times 1. So we get X minus 1/2 for U2. Okay. And so just to say it again, this is 1/2. So the numerator is 1/2, the denominator is 1, this is a 1. So altogether we got 1/2. And for U3, what we're going to get is, let's see, we'll have V3, so that's X squared, minus the projection of V3 on W2. So this means that we're looking at X squared minus the projection of X squared on U1 minus the projection of X squared on U2. U2 was X minus 1/2. Okay, so I have a little bit of calculating to do here. So this is going to be X squared minus the inner product of 1 with X squared divided by the inner product of 1 with itself times 1 minus the inner product of X squared with X minus 1/2 divided by the inner product of X minus 1/2 times X minus 1/2 times X minus 1/2. Okay, and so that's the idea here. And then these inner products, so 1 with X squared is going to be the integral of X squared from 0 to 1. So that's going to be 1/3. The inner product of 1 with itself is just 1. And then we need to compute the other ones too. So we have the inner product of X squared with X minus 1/2. That's going to be the integral of X squared times X minus 1/2. And let's see, that's going to be the integral of X cubed minus 1/2 X squared. And so that's going to be 1/4 minus 1/6. So help me out here. This is going to be, if you were in class, I would ask for your help with the algebra here. This is what, so I guess our common denominator here is 12ths. So this is 3/12 minus 2/12, so 1/12. So that's the inner product of X squared with X minus 1/2. And then we still need to compute the inner product of X minus 1/2 with itself. So that's going to be the integral of X minus 1/2 squared from 0 to 1. So that's going to be the integral of, let's see, X squared minus X plus 1/4. So that's going to be 1/3 minus 1/2 plus 1/4. So again, I would ask for your help, but I can't have it. So what do we got here? We have, it looks like 12ths again. So this is going to be 4/12 minus 6/12 plus 3/12. And so that also happens to be 1/12. Okay, let me just check that I did that right. I think that also happens to be 1/12. Yep. And so minus 1/12 over 1/12 times X minus 1/2. So remember, this is U3 that we're computing. So this is X squared minus 1/3, and then minus the quantity X minus 1/2. So altogether, this is x squared minus x, and then plus 1/2 minus 1/3 is plus 1/6. Okay, and so our orthogonal basis is 1, x minus 1/2, and x squared minus x plus 1/6. And you can check if you take these inner products, you really do get 0. These really are orthogonal with respect to that inner product, where the inner product is the integral from 0 to 1. So that is the orthogonal part. And then what we need to do is compute the length of the vectors. Well, the length of the vector here, so if I take this quantity squared, so the inner product of 1 with itself is going to be the length of 1 squared. So that's the integral of 0 to 1 of 1 dx. So that's 1. So that's, again, already unit length. The inner product of x minus 1/2 with itself is what we computed in this step here. So that happened to be 1/12. So this was, this is the length squared. So that means that the length of u is going to be, so the length of the vector u2 is going to be 1 over square root of 12. So that's going to be what? 1 over 2 square root of 3, just to make the algebra a little nicer. And then finally, we have this annoying one to look at, x squared minus x plus 1/6. X squared minus x plus 1/6. And so if we expand this out, we're going to get x squared minus x plus 1/6 squared. And so let's think about what that's going to be. We're going to get x to the 4th. So we're going to have to do a little algebra here. This is a Calc 1 problem, but an annoying Calc 1 problem. X squared minus x plus 1/6. So we get x to the 4th. We get minus x cubed, so that's minus 2x cubed. Okay. For the x squared terms, we're going to get x squared times 1/6, and then minus x squared. So that's going to be 1/6 plus 1/6 is 1/3. Minus 1 will be negative 2/3 x squared. The x terms we're going to get from negative x times 1/6, negative x times 1/6. So that's going to be negative 1/3. Let's make sure I did that right. Negative 1/3 x. And then plus 1/6 over 1/6 is 1/6. And so if we compute this out, we're going to end up with 1/5 minus 2/4 minus 2/9 minus 1/6 plus 1/6. And that's going to end up being, let's see, we're going to get 1 over, well, we just need to do it. So the those cancel. Something is wrong here, though. Something I'm really bothered by it. And that's the signs. So I think I found a mistake here. So we had, in computing our x squared terms, we had 1/6 x squared, 1/6 x squared. It should be plus x squared. So that was 1/6 plus 1/6 plus 1. So that's 1/3 plus 1, or 4/3. So it should be a plus 4/3. And therefore, when we integrate, we'll get 4/9. So that should be a plus 4/9. That makes me happier, because now the integral is positive. We know that because it's an inner product, the integral should be greater than or equal to 0, and it should only be 0 if it's the 0 vector itself. Anyway, so we get, let's see, 1/5 minus 1/2 plus 4/9. So that's going to be, it looks like our least denominator will be 90. Okay, and I'm still not perfectly happy with that. But this is going to be 18 minus 45. So 1/2 is 45 over 90. And then plus 40. Something still seems just a little bit off here. This is 58 over 90 minus 45 over 90. So 13 over 90. Let's check one more time. Sorry to make you walk through the algebra with me here, but we get x to the 4th, so fine. Minus x cubed minus x cubed, so minus 2x cubed. X squared, so 1/6 plus 1/6 is 1/3. It's 2/6 or 1/3 plus x squared, so 1 and 1/3, so that's 4/3. And then let's see our linear terms. We had negative 1/6 x, negative 1/6 x. So that is negative 1/3, and then plus 1 over 36. Ah, there's our error. It should be 1 over 36. So that was minus 1/6 plus 1 over 36. We already did the work of the first few. So this is minus, let's see, we can't write 36 as being over 90, but we can write it as being over 180. So we'll deal with that in a second. So that's minus 1/6 plus 1 over 36. So this is, so the first bit we said is 13 over 90 minus, let's see, 1/6 is 15 over 90 plus 1 over 36 is 5 over 180. So this is negative 2 over 90, so negative 4 over 180 plus 5 over 180. This is 1 over 180. That I think is right. Okay, so there we go. So the norm of the vector u2 squared is 1 over 180. That means that the norm of the vector is 1 over the square root of 180. So this is, let's see, the largest square that we can bring out is, let's see, we can definitely factor out a 9 and 4, so 36. So this is going to be 1 over 6 square root of 5. Okay, and so now we're ready for the orthonormal part of this. So E1 is just going to be 1 because this is already unit length. E2 is going to be U2, which we said was x minus 1/2 divided by its length. So that's a 1 over square root of 12. And then E3 was 1 over 6 square root of 5 times whatever it was, x squared minus x plus, I've already forgotten what it was, 1/6. Okay, and now these are your orthonormal basis for P2 with this inner product. Okay, so again, same idea, same process. I kind of like thinking about this in terms of the span of W1 and W2 rather than thinking about the span of the individual vectors, because it's easier to remember, right? It's easier to remember why this works and how it works, I think, when we think of these as the subspaces. The last comment that I have in this video, and then we're going to be done talking about Gram-Schmidt for arbitrary inner product spaces. But the last comment that I have for this video is that if you change the inner product space a little bit, so let's say we're still talking about the polynomials with real coefficients of degree n or less. If you change the inner product, though, to be the inner product of f and g to be the integral from -1 to 1, it turns out there's some nice, good reasons for that. And the polynomials that you get, so you can start with the standard basis, 1x, all the way up to x to the n. This is an n plus 1 dimensional vector space, P sub n. And it turns out that the vectors that you get by applying the Gram-Schmidt process to the standard basis have special names, and you might see them, so I wanted to say it. So these are called Legendre polynomials. Okay, so Legendre polynomials give you a orthonormal basis with respect to this inner product for the n degree polynomials. Okay, so that is just a really famous set of polynomials that seems to come up all over the place. Again, lots of things in math are unreasonably effective. Legendre polynomials are there. So that's the idea there. Okay, so that's all I wanted to say about Gram-Schmidt and inner product spaces.